Hello, this is a makeup lecture for our 6th week material in electrical machinery 1 course about transformer tests. There are 3 types of tests: polarity test, open circuit test, and short circuit tests. Actually, I should remove the tests at the end. Polarity test is the simplest and requires less equipment. Open and short circuit tests are more elaborate, and they find uh, exact equivalent parameters of the transformer in, of course, in experimental errors. The transformer polarity test is a kind of finding the dot convention point of the primary and secondary. So if you apply a waveform to the primary, you get a transformed voltage at the secondary. If the polarity is as shown on the left side, the let's say the cycles are in phase. Actually, positive at positive cycle, we receive the positive cycle at the secondary as well. If the dots are reversed, we have 100-degree phase difference or negative voltage. So this is the full scheme of the polarity test, but actually V1 and V3 are not so necessary because they are straightforward. They measure the primary voltage and secondary voltage, which you already know it. V2 is critical. If, as shown, the dot convention is as shown, that means V1 equals to the positive and negative sign-wise addition of V2 and V3, then this is the case, and V2 is the difference voltage between V1 and V3. You get the equation at the bottom. Actually, that's a magnitude-wise and, let's say, phasor notation kind of addition, because not all voltages are exactly in phase. There are some slightly phase differences among that, but that can be neglected. So if you neglect, you just add the RMS values. So V2 in this case is the difference between V1 and V3. And if the dots are reversed, you see V2 is the addition of these two voltages because of the, let's say, correct or additive summation of the V1 and V3 or primary and secondary voltages. So the value at the V2 determines the dot convention. And there's a nice demonstration experiment already uploaded to star environment, and homework number 4 is given accordingly to find some parameters about the given real transformer results. Now let's come to the second transformer test. This is called open circuit test. Why? Because we apply some voltage and some test instruments are placed at the primary side and secondary side is left open. So this is the reason the secondary side is open. There's no load. It's called open circuit test. In this test, the load side is empty, not connected. Load current, secondary current is 0. So you just apply voltage and measure current, voltage, and power at the primary side to get the values of the core components of the equivalent circuit. In other words, series components of resistance and inductance at the windings are so small compared to core or shunt components, they are neglected. So actually, roughly, with a little error, you find the shunt components of the equivalent circuit while the load side is fully unconnected. So accordingly, you measure 3 values: V open circuit, I open circuit, and P open circuit. From these values, the resistive component of the shunt branch can be calculated by the power and voltage values from the measurement instruments. And the current, from the current, okay, You calculate the full current through here. So if you subtract the resistor current from the total current, of course, that's a vector quantity. So you should be thinking real and imaginary parts. You can calculate the current through the inductive branch of the primary side or open circuit side. So basically this is the general circuit diagram in more simplified form. You measure three quantities: voltage, current, and power. And then by using these formula, for example, from power to V divided by V squared gives the conductance or 1 over resistance of the shunt branch. If you know this, you can calculate the current through it. This current through the inductor is 90 degree out of phase or lagging. This current, you know this. And the amount of total admittance of this branch is I open circuit over V open circuit. These are known quantities. And you certainly find at the end, find the inductive admittance of the branch expressed in minus JBM. You can express the same thing as plus JX of M as well. So conversion is very straightforward. So these open circuit test basically gives the high voltage side shunt parameters. The second test is short circuit test. This time you short circuit the transformer at the load side. But you should be careful because in the previous test you can apply rated voltage to the primary. But in short circuit test, this can burn the transformer, so you never applied rated voltage to the primary. You apply maybe 10% or 20%. You get the rated current at the secondary and then stop increasing the primary voltage. So basically this time the load is short circuit. Most of the current passes through windings. Very little current, since primary voltage is low, very little current flows through the shunt branch. So you can, in these tests, the shunt branch current is neglected. The calculations are easier. So by using the same components or instruments, measuring instruments, voltage, current, and power. Okay, so this is the node of applying low voltage. So this is the equivalent circuit of the short circuit test. These are the measurement instruments. At the left side, 10 or 20% rated primary voltage application. Now, these are the referred impedances, resistive and inductive reactances referred to the primary side, and the load is short-circuited. So full current passes through them, and the power is lost in these two resistors. One is primary winding resistance. The next one, R2 prime, is referred secondary winding resistance. So from the power equation, from I square R equivalent equals to the real power, you can calculate R equivalent. R equivalent is the sum of these two. You cannot calculate which part belongs to R1 or R2 prime. Just, it's a convention that 50% is R1, 50% is R2 prime. When you refer R2 prime, you have to divide by n squared. Don't forget this. So after calculating R equivalent, you also can calculate the full impedance by using the voltage, short circuit voltage divided by short circuit current, and you find the whole impedance of the windings. Then by using the impedance triangle, you can subtract R equivalent from this value and you obtain the X equivalent. Again, half of it is x1. The other half of it is x2 prime. So you can find the winding components. Note that when you are doing measurements or experiments with AC, then actually you are measuring or utilizing 10% more than its DC resistance in a certain wire or element. So this is how we obtain the equivalent circuit of a transformer presented in the previous week. So primary and secondary side winding resistances and inductances can be calculated, and core loss or shunt components can also be calculated by open circuit test. So at this diagram, we see the equivalent circuit of a transformer connected to a load at the right side and energized with an AC source denoted by red power input sign. So this is the whole power transformer circuit. Now our aim is to have the best power at the output load. So all these elements, actually resistors, are the power dissipators. So transformers, power loss components. Inductors are reactive power loss components. So these are all equations, including voltage and current and power factors, their phasor diagrams. The real power at the input is multiplication of voltage and current, again multiplied with a power factor cosine theta 1. And input power actually is the sum of all power loss in these three resistors, as well as main power delivery to the load. So these three power elements on the resistors are loss components. These are called copper losses as well. So that's the reason you see P of Cu1, copper loss 1, etc. And core power loss is given by the voltage across this shunt branch times the conductance at this branch. So that shunt branch is not exactly the primary voltage, but sometimes you neglect the voltage drop across these things, and an easier calculation. We will demonstrate it in an example later. So this can be simplified by approximation. This is called approximate equivalent circuit. So primary and secondary winding resistance are superimposed. So we have only one series impedance and we have one shunt branch. So this is the phasor diagram. Always voltage at the load is taken as a reference. So this zero phase angle is our load phasor. Now there are two voltage drops at the inductor and resistor. They are given in these two vectors accordingly. So this is with the same phase of the load current. Okay, so this is the load current, and assume this is a lagging or resistive and inductive load. Okay, so this is the potential drop across the resistor. Why? This is in the same phase with the current. And this is the load voltage is 90-degree leading that current. This part is inductive voltage drop. So the vector sum of all gives the V1, which is the voltage at the input or primary. You see, actually this is a little bit exaggerated because this part is normally the magnitudes are quite lower than shown, but in order to see it clearly, that was exaggerated. We come to the first definition about the quality of the transformer. That's voltage regulation. Voltage regulation is the voltage between these two voltages, load voltage and primary side voltage, divided by rated load voltage. So regulation 0 is the best situation, perfect situation, but it cannot be attained. Normally, a couple of percent regulation is very good in practical life. You can also have 0 regulation under certain circumstances, but this is achieved when your load is capacitive, which is not realized in real-time environments. There is a nice derivation of that, so that's left as an exercise for this video, plus homeworks may be given accordingly, but derivation is as shown in this slide, so you can study by your own. Actually, 0 regulation does not mean that the voltages are exactly in phase. No, their magnitudes are equal, but their phases are different. How did we realize that? When the load current is leading the voltage, the resistance voltage drop is again with positive angle. 90-degree ahead inductive current is also leading. That results in same magnitude V2 and V1 prime. And this is verified. Another quality factor for the transformers is efficiency. Efficiency is defined as it's a percentage value, unitless, output power to the input power, or output power or over output power plus losses. You remember in transformers, we did have 3 loss components. These loss components are on the transformer equivalent circuit resistors. So by knowing the values of these resistors, refer to the primary side. How do you understand it? This one is R1, primary resistance. This one is R2 prime. So R2 or secondary side is referred to the primary. So this is the exact equivalent circuit, and those are the loss components. Also, we refer the load to the primary to simplify the equivalent circuit. So with efficiency, if you know all voltages and currents and resistor values, you can easily calculate the power loss on resistors, I square R losses, or V square over R on these series or parallel components. So there are some little approximations. The voltage phasors on primary voltage or shunt circuit voltage or low voltage, sometimes you can take the same. For efficiency calculations, you may use the same number, but we will give an example here so that there's not much difference than using approximate equivalent or exact equivalent circuit. So this is our example. You should always consider that this current is in the same phase with the voltage, or this current is 90-degree lagging the voltage at the inductor. Now let's look at some examples. Something maybe quite good in some sense. Okay, there are some 3-phase circuits, and with the transformers, or an example from one of your textbooks. So this is actually a transformer and drawing the equivalent circuit of it, and the values are given. So this is like decoding the problem, some values and corresponding circuit elements, admittance or inverse admittance, which means the impedance kind of expressions. So this is a very good self-study. And with the given values, the exact equivalent transformer can be constructed as is. So this is the core part with the ideal component and the core loss components, and the numbers are given. So be careful about these numbers. They can be referred, or you have to refer by multiplying or dividing n square accordingly. So these are Cartesian coordinate expressions, okay, for the impedances. And this is another example. Again, utilizing the equivalent circuits. So these are left as an exercise for this part. And in one specific particular example, two methods, exact equivalent and approximate equivalent method results are compared. For example, this is the question. A big transformer, turns ratio 10, calculating the efficiency by using the approximate equivalence circuit. But instead of approximate equivalent, if we use exact equivalent, then we have to do more calculations. Why? Because this resistance, or due to the voltage drop of this impedance, primary voltage and the shunt equivalent part voltage will not be the same. Neither of them will not be the same with the load, but still the same problem is solved. And finally, we find very small solution difference with the increased cost of time to solve, less than 1% discrepancy. So approximate equivalent circuit solutions would be okay. So there are more examples, either from the exams in the previous years or homeworks, or our handwritten notes, etc., are waiting for you to study through. So thanks for joining my online lecture tutoring. And I wish you the best health and good luck in the courses.